this lesson, we're going to explore the applications of derivatives in terms of particle motion. So we're going to be looking at the velocity and the acceleration when given a position function. We're also going to look at how to figure out when a particle is at rest or moving in a certain direction, whether left or right. And then we're going to explore what it means for a particle to be speeding up or slowing down. So the first thing we want to look at is how are position, velocity, and acceleration related. So the position function is x of t, and sometimes they use s of t instead of x of t, but they mean the same thing. And then position is measured in units of length, so feet, miles, meters, depends on the situation. Velocity, which is v of t, is the derivative of the position, so it is equal to x prime of t. It's measured in units of length per unit of time, so it's miles per hour, feet per second, things like that. And then the acceleration, which is a of t, is the derivative of the velocity, or the second derivative of the position. And that's measured in units of velocity per unit of time, so feet per second, or we could call that feet per second squared. So there's this diagram that we're going to draw a little bit later when we know all the things of calculus. But right now we can draw the top half. So we have position, which is x of t, we have velocity, which is v of t, and we have acceleration, which is a of t. Okay, so we have to be able to get from the position to the velocity and from the velocity to the acceleration. And the way that we go from one to the other is by taking the derivative. So I'm going to put d over dt since this is going to be in terms of time. Okay, so we know the top half of this. We'll figure out the bottom half in a later lesson, but this will kind of maybe help you figure out where they are. So it's position, velocity, acceleration, and you have to kind of go from one to the other by taking the derivative. So let's look at an example. So here we have the position of a particle is given by x of t is equal to t cubed minus 6t squared plus 5t plus 30, and t is measured in seconds, and x of t is measured in inches. Find the velocity of the particle at t equals 3 seconds. So we're going to take the derivative because v of t, which is our velocity, is equal to x prime of t. It's the derivative of the position. So if I take the derivative of this, this is going to give me 3t squared minus 12t plus 5. And I want to find the velocity. So we already found the velocity function at t equals 3 seconds. So we're going to do v of 3. And all we're going to do is plug 3 into my t. So 3 times 3 squared minus 12 times 3 plus 5. And this is going to give us -4. And the units that we're using is going to be inches per second, since we had inches for our x and seconds for our t. So -4 inches per second. Okay, let's look at another example. So here we've got the position of an object is given by x of t equals cosine of 3t minus sine of 4t. Find the acceleration at t equals 0. So now we're trying to find the acceleration. So first thing I have to do is find the velocity. So I'm going to take the derivative of the position. So v of t is equal to x prime of t. So the derivative of this, I have to use the chain rule. So I'm going to get -3 sine of 3t, and then I'm going to get -4 cosine of 4t. So that is the first derivative, that is the velocity, but I need the acceleration, so I'm going to find the acceleration by taking the derivative of the velocity, which is the second derivative of the position. So you don't need to write this out every time. You could just write the a of t is equal to v prime of t, but for right now I'm just showing you that it's related to the original. So again, I'm going to use the chain rule. So this is going to give me -9 cosine of 3t, and this will give me plus 16 sine of 4t. So now I want to find the acceleration at t equals 0, so I'm just going to do a of 0. So -9 cosine 3 times 0, so 0, plus 16 sine of 4 times 0, which is 0. So when I go to solve this, this is just going to be negative 9 times 1, so negative 9, and then 16 times 0, which is just 0. So we end up with negative 9. Now notice that this problem did not give me any units. So if the problem doesn't have units, you don't have to have units in your answer. Okay, so this is just negative 9. All right, so let's look at one more that's a little bit different. So let v of t equal 1 over pi plus sine of 3t, and represents the velocity of an object moving on a line. So here, instead of being given the position function, we're given the velocity function. On the interval from pi over 2 to pi, what is the velocity when the acceleration is 3? Okay, so we first need to figure out what the acceleration function is. Since we're given the velocity function, all I need to do is find the first derivative of this. So a of t is equal to v prime of t. So when I take the derivative of this, 1 over pi is just a constant, so I'm going to get 0 for the derivative. And then I have sine of 3t, which I'm going to use the chain rule. So this is going to give me 3 cosine of 3t. So I want to find the velocity when the acceleration is 3. So I need to solve for the t value when the acceleration is 3. So I'm going to do 3 cosine of 3t, so that's my acceleration. And when does that equal 3? So I can divide by 3, so I get cosine of 3t is equal to 1. So I need to figure out the cosine of what is equal to 1. So the 3t that's inside, the only time I can get 1 is any iteration of 0 and 2 pi. So I'm just going to write, so I'll just put cosine of like 0 is 1, and cosine of 2 pi is 1, and 4 pi and 6 pi and all that stuff. But notice the interval, right? So the interval is between pi over 2 and pi. So I have to figure out, what does t have to be? So 3t has to be 0, and 2 pi and 4 pi and things like that. So I'm going to set, let's go over here. So I'm going to do 3t, and I'm going to set that equal to 0. Well, if I solve this, I get t equals 0. That's not in my interval, so I can't use that. If I take 3t and I set it equal to 2 pi, right, because that's the next time that we get the cosine being 1, I divide by 3, so I get t equals 2 pi over 3. Okay, that is within the interval, so that's good. If I try to go for another iteration, let's say 4 pi over 3, I'm going to get, it's not 4 pi, 4 pi, sorry, I'm going to get 4 pi over 3, which is outside my interval. So the only t that's going to work here is this 2 pi over 3. So this is the t value that gives me an acceleration of 3. So now I want to find the velocity at that. So I'm going to do velocity at 2 pi over 3. So I'm going to plug that into the velocity function. So I get 1 over pi plus sine of 3 times t, and t is going to be 2 pi over 3. So what I get here is 1 over pi plus sine of 2 pi. And sine of 2 pi is going to give me 0. So I end up with just 1 over pi. Okay, and again, this doesn't have any units involved, so we're just going to leave it as 1 over pi. So what can the velocity tell you about the object? So the object itself is at rest when the velocity is equal to 0. An object is moving to the left when the velocity is less than 0. So when velocity is negative, the object is moving to the left. And an object is moving to the right when the velocity is greater than 0, or when the velocity is positive. So if I just go back real quick, where was it? Right here. The velocity I got was negative 4 inches per second. Okay, that means that it's really moving to the left 4 inches per second because it's negative. Okay, so it's okay to have negative values. Just make sure that you understand that the negative means that it's moving to the left. Okay, and then how is speed related to velocity? Okay, well, speed is the absolute value of velocity. Okay, so speed always is going to be positive. An object is speeding up when the acceleration and the velocity have the same sign. So if you're looking at a graph, it means that it's going away from the x-axis. An object is slowing down when the acceleration and the velocity have opposite signs, which is going towards the x-axis. So if I just look at a quick, oh my gosh, really bad graph here. Let's say that this is going to be the graph of the velocity, so v of t. Okay, so I have a positive velocity if I'm above the x-axis. And if I have the acceleration, that's the slope. So I'm just going to draw random lines here. So right here, it's above the x-axis, so the velocity is positive. So I'm just going to make this red. So v of t is greater than 0 because it's above the x-axis. And a of t, the slope of the velocity, is also positive. So this is going to indicate that this is speeding up. And you can see on the graph, it's moving away from the x-axis. So that's speeding up. Another way to think about speeding up, it could be going like that. So in this case, in blue, v of t, our velocity, it's below the x-axis. So it's less than 0. The acceleration, which is the derivative of the velocity, which is our slope, is negative here. It's less than 0. So again, they're the same sign. It doesn't matter if they're both positive or both negative. It matters that they're both the same sign. So this would be another example of it speeding up. And we can see again from the, ooh, that's a bad D, speeding up. I'll just draw little arrows here, right? It's moving away from, the x-axis. So as it moves away from the x-axis, it speeds up. If I were to look at it the other way, where like, I'm going to draw an arrow like that, right? This green arrow, this is where, let me get rid of this so it's not confusing. The green, it's above the x-axis here, so the velocity is greater than 0. And then the acceleration, which is your slope, is negative. So they're different signs. One's positive and one's negative. So that means it's going to be slowing down. And then same idea if I did something like that, right? So again, the green and the purple, they're going towards the x-axis, whereas the red and the blue are going away. So this purple one, it's below the x-axis, so the velocity is going to be less than 0. And then the slope is positive here, it's greater than 0. So the signs are different, so this is going to be slowing down. Oops, slowing down. Okay, so sorry if this is a little bit confusing, but basically, if it's going away from the x-axis, it's speeding up. If it's going towards the x-axis, it's slowing down. You're comparing the signs on the velocity and the acceleration. So same sign, whether they're both negative or positive, speeds up. Opposite signs is going to slow down. So let's look at this example here. A particle moves along the x-axis. The position of the particle in feet can be modeled by x of t equals this thing. And it's between 0 and 5, where t is measured in minutes. When is the particle at rest? Okay, so when the particle is at rest, that means that the velocity is equal to 0. So what we need to do first is find the velocity. So I'm going to take the derivative of the position. So velocity is going to equal t squared minus 5t plus 4. And I want to set it equal to 0. Here we have a regular quadratic that we can just factor. So I'm just going to draw a little arrow over here. If I factor this, it's going to be t minus 4 and t minus 1, and that equals 0. So I solve and I get t equals 4 and t equals 1. So I'm going to write my answer and just say, well, that could be my answer. I'll just write it over here a little bit neater. So t equals 4 and t equals 1. And I'm going to give a justification. Even though it doesn't say to, I want you to just be aware of why it is. So t equals 4 and t equals 1 because, I'll just put BC, because v of t is equal to 0. And I'm just going to box this, hopefully not mess it up. Whoops, there we go. Okay, so the particle is at rest at t equals 4 minutes and t equals 1 minute because the velocity is equal to 0. So let's look at the next part. When is the particle moving to the left? So if it's moving to the left, that means that the velocity needs to be negative. Now notice that we got 4 and 1, and that's where the velocity is equal to 0. So those are our critical points. So if we think about this as a normal first derivative, right, we have, let's say, x and v, like x of t and v of t. I'm going to make a sign chart. So it's the same type of sign chart I would make with f and f prime, but I'm just using like x and v. So this is really not straight, but that's okay. So we have 1 and we have 4. So I don't really care about the top piece. I don't care if it's increasing or decreasing the position. I care about the velocity sign. So I could fill in the top with arrows, but I'm just going to really focus on the bottom here. So if I pick a value that's less than 1, let's say 0, remember that we're plugging it into the simplified derivative. So I'm going to plug it into like this piece over here. So if I pick a 0 and I plug it in, what I'm going to get is a positive. Okay, if I pick a number between 1 and 4, so let's say 2, I'm going to get a negative. And if I pick a number greater than 4, let's say 5, I'm going to get a positive. Okay, so you could fill this in with like increasing, decreasing, increasing if you want to. But the velocity is going to be negative on the interval from 1 to 4. So when is the particle moving left? It's moving left from 1 to 4. And again, I'm just going to justify it, even though it doesn't say it, because v of t is less than 0. So it's moving to the left because the velocity is negative. It's less than 0. Okay, and then this last part, at t equals 3, is the particle speeding up or slowing down? Justify your answer. So in order for me to figure out if it's speeding up or slowing down, I need to figure out the sign of the velocity and the acceleration when t is equal to 3. So I already have my velocity equation. So I'm going to just find my acceleration function here by taking the derivative of the velocity. So this is going to give me 2t minus 5. Okay, so I know a of t is that. I know v of t, I'm just going to write this here. I don't know, so I wrote it backwards, I guess. T squared minus 5t plus 4. Okay, so I want to find both of these evaluated at 3. So I'm going to do v of 3 first. So I'm plugging 3 in for my t. So this is going to be 3 squared minus 5 times 3 plus 4. And I don't really care about the number. I care about the sign. But we can figure it out anyway. Like, so 9 minus 15 is negative 6 plus 4 is negative. So I just care that this is, let's not put equals here. Let's put just less than. Okay, so this is going to be less than 0. So that means that my velocity at 3 is a negative number. I'm also going to find my acceleration at 3. So I'm going to plug 3 in for t. So 2 times 3 minus 5. 6 minus 5 is a positive number, so that's greater than 0. So since the velocity is less than 0 and the acceleration is greater than 0, they have opposite signs. So that would mean that this is slowing down. So slowing down. And the reason being, this one does say justify your answer. So it's slowing down because v of, well, let me change this, v of 3 and a of 3. So you can write this, or you can write velocity and acceleration have opposite signs. All right, and that's our reasoning. So since we have opposite signs, it's slowing down. Okay. So now we're just going to look at 2 other examples where we don't have the function, so we have to use knowledge of other information in order to figure things out. So here we've got Tina, who's completing a 50-minute training run on a straight path to prepare for her upcoming marathon. Her velocity is given by a differentiable function v of t, where v of t is measured in meters per minute and t is measured in minutes. Selected values of v of t are given in the table below. So notice we don't have a function for the position. We don't have a function for the velocity. All we have are these numbers in this chart. So part A says estimate Tina's acceleration at t equals 10 minutes. Indicate proper units in your answer. So we're given the information about the velocity. We want to find the acceleration at t equals 10. So acceleration is the derivative of the velocity. So the derivative, remember, is the same thing as the slope. So we will say, let me write this over here, a of t is equal to v prime of t, right? That's what we're going off of. We know that the acceleration is the derivative of the velocity, which means slope. So I'm just going to use this as points on a line, right? So I have a of t, the acceleration at, not t, a of 10 is the acceleration at 10, and I'm just going to find the slope of the line. Now 10 would be somewhere in here, right? So I'm going to use these two values as my points because I want to pick the points that are closest to 10, which is what I'm going for. So I'm going to have v of 15 minus v of 5, so change in y over the change in x, so 15 minus 5. So v of 15 is 220, v of 5 is 170, 15 minus 5 is going to give me 10. All right, so here I get 50 over 10, which is equal to 5. And then we wanted the proper units as well. So since the velocity is meters per minute, on the top here I have meters per minute, and on the bottom I have minutes. So I'm going to end up with 5 meters, this is really bad, per minute squared, or meters per minute, however you want to write it. That would be the proper units. And then for part B, must Tina have switched directions in any of the subintervals indicated by the table, and explain why or why not? Okay, so remember that a positive velocity means that going to the right, and a negative velocity means going to the left. So when we look at this chart, we can see that right here, the velocity is changing from positive to negative. And then again, here, the velocity is changing from negative to positive. So since the velocity is changing signs, that means that Tina is changing directions. So we'll say that, must there be a time? We'll say yes. And then we can say on the interval from 15 to 32, right, between 15 minutes and 32 minutes, and between 40 minutes and 50 minutes, right, she's going to change direction, and that's going to be because v of t changes signs. So whenever the signs change in the velocity, that means that the person or object changes direction. Okay. And then the last one we're going to look at, again, we're not given the function, but here we have a graph. And note that this is the graph of v of t. So this is our velocity graph. And it represents the velocity of an object moving on a line over the time interval from 0 to 8. Okay, so when is the object at rest? And justify your answer. So when an object is at rest, the velocity is equal to 0. So since this is the velocity, where is this equal to 0? Well, that's equal to 0 here and here. So we'll say that t is equal to 5 and t is equal to 8. And justifying my answer would be because v of t is equal to 0. So we'll just box that. Okay, and then the last one, at t equals 2, so let me just get rid of these. At t equals 2, is the object speeding up or slowing down? Explain your answer. So here, I'll just put a dot there. There's where t is equal to 2. So a couple of things I notice. If you think about where it's approaching, is it going towards the x-axis or away from the x-axis? The line that t of 2 is on is going away from the x-axis, so that means that it's going to be speeding up. And we can kind of just write this out a little bit. So we know that the v of 2, right, if I look at v of 2, that's like 1 point something or other. So that's going to be greater than 0. A of 2, the acceleration at 2, which is the slope of my velocity, I can see the slope is positive, right? The slope is going up, so that is also greater than 0. So since my signs are the same, that means that it is speeding up. So we'll say speeding up, and that's going to be because velocity, so I'll put v of t, or v of 2, because it's specifically at 2. So we can either write the word velocity, or we can say v of 2, and the acceleration, or a of 2, have the same sign. And again, you can also see it based off of the segment of the line is going, away from the x-axis, because it's above the x-axis and has a positive slope, meaning they're the same sign.